Okay, Sarah. Hey, so did you get a dress for the party yet? Oh my gosh, less than a week. Here, you have to do the eye count for you. That's the one. I love it. You should
Yeah. You have
500 points. What is the answer? A. Dixon.
Millard Fillmore.
Millard Fillmore is correct. Now it's 200 points. How many push-ups does Chuck Norris do?
Excellent. Hello, everyone.
Hello.
To MS 531 and 131 computational camera. I'm Ramesh Raskar, remember, at the Media Lab. Nobody without a microphone. Can you hear me better? Excellent. So welcome again to the class, those of you who are here, our colleagues at Vortex in Moscow, and also hundreds of folks watching this class either phase shifted right now or possibly time shifted later on. And we're going to talk about many types of cameras in this class. Cameras that only a few years ago seemed limited to applications in military or extremely complex industrial settings or scientific settings. And now, as you can see, they are low cost enough and widespread enough that we feel safe to just leave them on the table right there, just like the breakfast here. And that's kind of interesting because this fusion of multiple spectrum, whether it's time or angle or polarization, is really coming together in the last few years. And so what we're going to do in this class is look at how these devices have come here, what's in them, and also think about the future of where these devices could go. What are some other technologies that could suddenly become highly dispersed and available to everyone? And nothing is off the table. But before we talk about the future, we should maybe spend a couple of seconds thinking about our past. So we have two lines here, and the natural question you have been asked before is which one is longer and which one is shorter? How many of you think the one on the right is longer? What about on the left? And how many of you think?
Equal.
One more time. I think the one on the right is longer. Absolutely sure. You will lock your answer? And that's how the world around us is evolving. Things we take for granted, things we thought are absolute truths and are not going to change, are changing while we are looking somewhere else. And so as much as we want to talk about the future, I think the very fundamental message for this class is to realize that everything in the past can unlearn and relearn when it comes to computational cameras. When we think about cameras, they run, at what frame rate does your camera run typically? 30 frames per second, 60 frames per second. You have seen some movies where The camera is running at 1,000 or 5,000 frames per second. But you can sometimes go even faster than that. Doc Edgerton showed right here at MIT that you can create pictures of a bullet piercing through an apple. An equivalent exposure time of about 1 microsecond. And then what about picture on the right? That's also a similar effect of a very short, strange exposure time. That's a real photo of a propeller blade. Do you know how that photo was taken? It was taken with a cell phone camera. Do you know why that shows up? It's because of rolling shutter. And as the blade is rotating, your actually camera is exposing only one row at a time very quickly toward the frame. And so although the rotor, the propeller blade is rotating as you would imagine, the way it's captured on the sensor looks extremely strange. So another message in this class is the way we see the world is very different from the way a camera sees the world. And sometimes that's a bug. Like rolling shutter is actually a cheat to avoid memory bandwidth and sensor bandwidth, but actually it can be also a feature, and you can use it in very interesting ways. And what about cameras that can go not 1 million or 1 billion, but 1 trillion frames per second? So this is some work from our group, where we're able to use scientific instruments in unusual ways to create slow motion movies of light in motion. Send a pulse of light into this bottle, and you can watch propagation of light through this bottle. So you have a packet of photons that are passing through this Coke bottle, and as the photons leak out from the bottle, you'll see some of them propagating on the table. Many of them reach the cap of the bottle. And if you watch the whole movie, you will see they'll explode, go in various directions. You will see a pocket of air at the top where the light is bouncing around. And you can see some really interesting effects. With that, we can start creating new type of photography, a new type of time-lapse photography where you can actually color code every few picoseconds of time steps. You can create cameras that can see the invisible. In this case, our obsession of seeing through a shower curtain. And it turns out by using spatial coding, using an ordinary camera but projectors that are projecting patterns, you can indeed start separating what's so-called direct bounce, first bounce, and what's because of second and later bounces. Decompose a single picture into these two layers. All right. Let me tell you a little bit about myself and my group. So I'm a faculty member at MIT Media Lab, and my group does all kinds of work in cameras and displays and playing with light and pixels. And we passed around some flyers for the group, so we can go in detail, but roughly clubbed as computational photography. We're playing with angle and polarization and speed. Femtophotography, we're looking at the world by observing the propagation of light. New types of 3D displays that don't require those funny glasses to see them. Medical devices that can exploit consumer technologies. New types of human-computer interaction. Another field that's emerging called visual social computing at the intersection of visual computing and social computing, and of course, a lot of theoretical and mathematical work on light propagation. And as I said, if you want to continue to challenge what we mean by a camera, what about a camera that can see around corners beyond line of sight? So we use our femto camera, the ultra-fast camera, shine light on the door. Some of the light reflects into part of the light reflects back on the door, and tiny fraction back at the camera, and that allows us to see around corners. And we haven't taken this device outside the lab.
No sound.
There are corners, but we cannot see at all.
Oi. Where else? Scientists trying to flood we have no sound. We have a sound. Ramesh, we have a sound. We don't Ramesh is trying to fix something.
Шумодат работает на тишине, он не заглушает звук.
We're trying to fix. Oh, what is
Yes, first day of class.
Yeah. Yeah, it's good. No. Can you say something?
Yes.
Can you hear us well?
Yes. We just lost our piece.
На их стороне, во-первых, работает шумодат, когда с нашей стороны тишина, точнее, с их стороны тишина, она как-то включается, чтобы правильный шум не мешал.
Presentation on mine.
So we can hear you well when you speak, but we don't see any English. Okay, it's working.
Давайте угадывать истории.
I swim into that.
Oh.
Excellent.
Sometimes even worse.
No.
Yes, I see.
Thank guys.
No, that's not.
You went around
Wait.
like 15%.
Go on again. Welcome. Go on again. Right.
Yeah, other students keep coming at the call themselves. That looks more like 90. I'm not sure. I mean, it's morning. Oh,
Do you still think we don't hear you? Нет, нет, не вижу. Так вообще, да. Самое лучшее, что ты пишешь,
То есть компьютер
отслеживает перемещение и записывает. Там, наверное, самое как лучше было, обычно смеешься, как обычно.
Ну, я просто не могу надеть ничего. У нас дома привык.
Кстати, кто может проводить?
Ребята, еще раз, маска слышно очень хорошо. Потому что нам не слышно, что они нас не слышат. Тихо.
И что?
За то, что ты говоришь, там все слышно. И ты им, может быть, мешаешь.
Я не знаю, все. Давай съеду. Как светит офигенно. С другой стороны, точно сложно. Еще
All right, we're back on. I think it was a good excuse for others to slide in while I was not watching. It's all about making visible invisible and invisible visible in class. And as I said, although we have only shown it in a laboratory setting, we could take this outdoors and build cars that can avoid collisions with what's around the bend, or start building endoscopes that are that can see deep inside the body beyond our cause. So let's talk a little bit about the structure of this class. As you know from the Stellar page, we're going to cover a very broad spectrum of how we play with cameras, some of the keywords that we have. And then this is a dense slide, but this is kind of the 13 lectures on how they'll be played out. So every lecture we have about 2 hours of presentations, myself and my co-instructors, who I will introduce very soon. And we also have about roughly 1 hour of lab time. So we're going to look at many areas. We're going to look at devices like Google Glass, or Kinect, or Leap Motion. We have many of these. You can play with them. In the lab, we will learn how to do programming on Android. We'll learn how to play with optics, how Lightro works, light-field cameras, what's the optical principles behind it, Fourier optics, wavefront coding, diffraction issues. And then we have a lab where we have a software simulation of some of these devices. and you can play with them yourself and create your own virtual optics software. We'll have an overview of computer vision by Dan Raviv, and we'll talk about principles of computer vision, and we'll have a fast-forward description of that, but also talk about how sometimes you can do really complicated operations with just a single command, because the libraries on PCs, on consoles, on mobile phones are becoming extremely powerful. And Intel recently introduced their perceptual SDK, and that's also another beautiful framework to play with computer vision. We'll talk about challenges and solutions in photography, such as high dynamic range, dealing with blur, how to capture 3D. And then in the lab, you'll be actually creating your own app for high dynamic range. We'll look at some of the sensors for high-speed imaging, camera arrays. Pelican Imaging is another hot company that's being discussed as a successor to Lightro that can capture light fields. We'll look at time-of-flight cameras that are becoming also very popular. Kinect right now, for example, is a stereo-based system that uses triangulation, but according to their announcements, Kinect from Microsoft is going to have time-of-flight. So this is something that used to, again, cost tens of thousands of dollars, and now it's available in form factors. The lab would be, you'll be actually calculating depth using such a time-of-flight camera. Beyond visible spectrum, looking at thermal IR, looking at multispectral imaging. Then we'll go into some math on compressive sensing, some image reconstruction techniques, tomography, and so on. And the lab would be on using deep blurring and deconvolution. This is a problem you would face for any camera application you would build. It's kind of the dark secret of some of these apps that we deal with focus and motion blur. We'll look at cameras for human-computer interaction, not just two-dimensional cameras. Most of the devices that you see, Kinect, Glass, Leap Motion, they're all two-dimensional sensors. But very soon, I'm sure we'll see sensors that are not just XY array of pixels, but are zero-dimensional, which is one pixel, one-dimensional, and so on. Augmented reality, we'll cover that. And one of the lab would be how to build a device that can see under your skin. That I like to have. I will have a midterm exam. It's open book, open text, open everything, open camera. So don't stress out about it. Some new topics in video blogging. We have a very strong research group. Nikhil Naik from my group, Dan Raviv, and also Daniel Kato, right here from my group are working on that. So they have a lot of data sets to work with. And we have some interesting devices that are coming up as well. When you think about online photo collection, one of the challenges for building application is how can you crawl online and actually collect some data sets? Go crawl on Flickr or some other databases and play with that. So one of the labs would be how to write a web crawler to get these pictures. And then we'll spend a lot of time throughout the semester thinking about the ecosystem of apps and what it means to create not just software applications, but also hardware applications. And we'll see many examples of that here. And these are attachments and how rapid prototyping is changing that world, as well as crowdfunding. One of our co-instructors is Rick Fulop, who's a very well-known entrepreneur himself, but now is a venture capitalist at Northbridge, and he looks at lots of such gadget-based companies. And he and I are also part of Start Labs here on campus, which promotes entrepreneurship. And then, of course, we'll have a grand finale with cheese and wine, but more importantly, your final projects. And as we told you, this class is being broadcast to our colleagues in Moscow, who didn't have to wake up as early as you. So they are more awake, I would imagine. But we also have hundreds of folks signed up online for this class, and many of them might become your teammates for either collecting more data sets or writing a software module, or if you yourself have not as strong a programming experience, but you have some ideas and applications, you can work with them and also do user studies with our individuals who are taking this class online. And we'll have a demo day and celebrate what happened. In terms of the structure, we have about 8 labs, so you'll be doing part of the work in the class, but we expect to spend 1 or 2 hours per week also finishing it up. And they're very quick assignments, as you can see. Writing an Android app or turning on an LED, writing a web crawler, will give you the skeletons. And each lab is about 5%, so that's 40%. The final project is very, very important because our goal is that you build a real app that goes out. Midterm exam, 20%, and class participation. And so my co-instructors are John Warner here, also wearing a glass. And he'll introduce himself a bit later. Rohit Puri, he's actually working on glass. He's doing some startups on glass. And then some of the mentors and assistants. I already mentioned Dan, if you can just raise your hand. And Nikhil Naik, and then Daniel. And these are experts in various fields. They'll be available throughout the class. And we'll have speakers who are from Google and Microsoft from those companies either stop by or join us online to tell about their own experience. And we'll also have some of the entrepreneurs who are writing apps for these platforms. Rohan is one of them himself, and of course some of the investors to keep it going. Any questions so far? The structure of the class, what we're doing here. You're on the right flight, but because we are about to take off. Good. All right. So what we'll be doing today is we'll talk about what exactly is computational camera. I will do a very quick walkthrough of different technologies, different commercial devices that are out there. Introduce you to John Werner, who will talk a little bit about how we're going to use the community. Then Dan is going to come and very briefly tell you about the type of computer vision and software we're going to use. Then Rick is going to, again, very briefly tell you about the cameras and app ecosystem. We'll do some demos, live demos, and I'll come back and talk about some other technologies that you might see. It's just a fast-forward preview. And we hopefully will have a first warm-up exercise today where you will go home with your first Android app already. Good. So let's get started. Finally, we can talk about the future. We have unlearned some of the concepts that you may have taken in law of physics. And if you think about the future, we want to ask questions like this throughout this class. What will a camera look like in 2, 5, 10, 20 years from now? How will billions of cameras change our social culture? We have about 20 to 30 million new people using a camera today worldwide. Individuals who have never used a camera in their lifetime, mostly because of mobile phones. But as you saw, all these devices are also becoming part of our life. It's like computing, we don't think of them as just these big boxes, but your computer is in your phone, in your car, it's in your microwave. If those of you use the lightning connector on your Apple machines that converts the Apple output to an HDMI output, that cable, the white cable, is actually a computer doing a real-time decoding and encoding of a video stream on the connector. So that itself is a computer, but we don't think of it. We call it a connector. We don't call it a computer. Your storage is actually a computer. And the same thing is going to happen with cameras. Right now, we think of cameras as easily identifiable devices, but they're going to become part of your life. They'll disappear, much like microwaves and cars, where we won't even call them cameras separately, but they'll be sensing, providing services. So definitely say bye-bye to your privacy. But there may be other solutions to overcome those privacy issues with technology. It's a catch-all market. What about image search? I feel one of the most pressing issue right now is to solve this key problem of image search. And we're talking about some computer vision issues. But how can we change the devices themselves and user interaction to actually simplify that problem? What about portable health diagnostics? And we'll be seeing some examples of so-called hardware apps that are attachment to mobile phones, or how Kinect is being used for health rehabilitation and so on. So, this worlds of engineering and life sciences are changing. And in fact, I'm teaching a class, co-teaching a class this semester called Engineering Health. Meets every Friday, so tomorrow is the first class. And it's very similar structure to this in the sense that we have lecture for 2 hours and we have lab, and we're looking at all the different technologies, from technologies like Kinect and time of flight and cars, but also other technologies that could become widespread, such as microfluidics, immunoassays, possibly PCR, and of course gyros and technologies for tricorder from Star Trek, to technologies for developing countries for health diagnostics. That class meets tomorrow, not here, but at MIT Media Lab. Will we live in a mostly virtual or augmented reality world? What will happen when our cameras run at 1,000 million billion frames per second, and the resolution is beating the microscope in nanoscopes? Can we improve trust in imaging? There was a time when we used to trust anything that's printed in black and white, and we lost trust in that very quickly. Then we had some trust left in photographs. That's visual evidence. We also lost trust in that. And right now we trust the videos a little bit, and that's going to disappear very soon as well. So again, how can we improve trust in that? Can we print anything? Right now we just print cheap plastic and toys, but very soon we might be able to print cars, or food, or even babies. This is the future. What are some opportunities in pervasive recording? What if you can open up Google Earth and zoom in, fly in, and see the world live? Not just that something that was recorded by, a truck that went around, once in 6 months, but it's live. When all these cameras are all over the place, anybody can tap into my stream, and if I can get paid, $5 a month, and bandwidth is taken care of, I might just share my stream for this. What about software like Photoshop? How is that going to evolve, given that our world is filled with multimedia and gigabytes and terabytes of data on a daily basis? How will we manipulate that? And of course, it's not just straightforward visual data, but there's also other metadata, like your GPS, your social network, even your finance data, your DNA, your biological data. And remember, you'll be using the same software to create babies. So, and what's the future of movie making and news reporting and sports viewing when every one of us has the same tool that these professionals have who are engaged in these activities? When every device, every phone is not just a TV, but a TV station that can broadcast. So think about Twitter, and your favorite celebrity has a Twitter feed, but just think about the day when your favorite celebrity has a glass feed, real time. What does it mean? And we'll look at some of those questions and be ahead of the game to see what kind of apps we can build. Any comments or questions? Does this all look reasonable? Yes.
Riots.
Istanbul riots. Like a GoPro or something like that. And was it live or recorded? Yeah. And I mean, news reporting is changing completely, right? If you look at all the terrible events going on in Syria and other places during Arab Spring, they almost exclusively relied on footage taken by folks on the street, because it's too dangerous in many cases to send dedicated stuff. Any other comments? Everybody feels comfortable with this future? Great. Okay. All right. So, as I said, what is disappointing though is that when all these companies think about cameras, they're looking at a very constrained way of capturing light. If you think about the world of biological creatures, successful vision, is that some of them are based on shadow, so they just have a hole and you can create a simple image. Or they have these compound eyes where individual straws can measure light. Sometimes they use lenses and it's refractive. In a single eye, you have a lens. and light is focused on the retina. But some underwater creatures use compound eyes. Sometimes they're apposition, which is one lens for one sensor, and sometimes superposition, which means more than one lens for one sensor, and sometimes reflective. I mean, if you look at a scallop, actually you get light reflecting back of the eye. That's actually a mirror, and then it's focused on the retina. The retina is actually in front of the mirror. And in case of lobsters, the mirrors are these vertical support structures. Light is reflected from them and focused. Right. Very unusual structures for that. So next time you're enjoying your seafood, think about that. Now, as I said, almost all the devices that you see here are in this corner here. Now, it's single-chambered, single-lens, a device that mimics human vision. Okay? That's kind of odd, because we should be able to use all these other mechanisms also to capture images. Because cameras are not just for taking photos and posting these photos on Facebook. I know that's the major application right now, but believe me, there's so much more going on in many other ways. Kinect, when it takes a picture, you don't care about looking at it as a photograph. It's providing information, creating depth maps, computing your skeletons, and so on. And we're going to get more and more of these devices that have nothing to do with, more and more of these sensors, camera sensors, that have nothing to do with photography. So think of that dimension. So we really have an opportunity to think about a computational camera that, as you can see, most of these devices are actually not focused on photography directly. Maybe Lightro here, and we'll talk about that. But Google Glass, time-of-flight cameras, leap motion that uses multiple illumination sources, PMD, which is time of flight, how long it takes for light to bounce from an object and come back, Xbox Kinect that uses stereo pair to create depth maps and articulated gestures, thermal IR cameras that you can buy in Home Depot, for a few tens of or hundreds of dollars, but could be in your cell phone in the next 2 to 3 years. Lightro, a light-filled camera that's angle sensitive, soft kinetic, paired up with Intel, I believe, and is going to be available also in very low cost. So this one you can buy already online for about $300, and very soon, or even lower than that. All right. So, what is traditional photography versus computational photography or computational imaging? In traditional photography, a ray of light comes in, hits the sensor, and that's pretty much the end of the story. But in computational camera, we're going to generalize everything. Light comes in, there is strange optics, strange lenses. Our sensor is generalized. It can sense light, time, polarization, angles. And we're going to take that data and then play with it, process it, and then use computational power, either available locally or over the network, using information that's available instantaneously, or using prior information, and create new imagery. And that imagery itself can be consumed by humans, or it could be consumed by other machines. So there are definitely 3 elements inside a computational camera: optics, sensors, and processing. But there's also something interesting outside, which is programmable illumination. And that could be modulated in space, time, angle, polarization, again, outside. So the world itself out there is actually very high dimensional modulator, because it can take this high dimensional incoming light field, reflect that in a very complex way, and we have to record it also in a very high dimensional way. Now, because of limitations on processing and bandwidth and memory and so on, we have to build our device in a clever way so that we're only taking a subset or subsample of this. So if you think about devices like a phone or a fax machine TV, all these devices evolved one by one. But imagine in 1950 you had said, phone is your TV, is your computer, and so much more, paperweight as well. And that's what's happening over here. We have a phone, we have a fax machine, we have a TV, and they're all doing different things, slightly different things, because they're all being geared for something slightly different. So one of the questions for us is, will we have a grand unifying device that will magically do all the sampling of all the dimensions? Because these are sampling, angle and time and polarization and so on, slightly different. So there's a interesting conversion coming up there as well. It's very much like, anybody here from telecommunication background? Or, so if you think about how you taught different channels like Wi-Fi and Bluetooth and GSM and CDMA, they're all different devices. But isn't it magical that all those communication channels are available within a single device, often on a single chip? And all those things that we're seeing on the board could merge into a single tiny device in the next 2 to 5 years. Okay, so let's move into some of these devices. I'll move through it quickly as just a teaser. We'll be talking a lot about class, of course, what it can do, and some of the possibilities. One common question people who don't think about optics is, how can you have a display so close and still be able to see it very comfortably? Do you know how? Does anybody have an analogy of how this works? How can you create a virtual image that's much further away? Sorry?
Focus approach.
Use some additional optics in front of it so that it appears very far away. Is there some other device that you use where the images appear very far away, although the physical image is very close? Sorry? Car mirror, but the physical object is still pretty far away. The viewfinder, absolutely. So I hope we have some viewfinders, because it's my favorite device. You can do so many interesting things with a viewfinder. So you have some slides of, your favorite animals or Star Wars characters, and you can just see the thing. But the actual film is right there. It's the same principle in some ways. Then there is Kinect, of course. And Kinect seems like a device that has interesting elements. It came from a company called Prime Sense. And I believe the co-founder of Prime Sense is now a student here at MIT. Is that still true? Is that true? I was told he's and it has 2 cameras. It has an ordinary camera, RGB. It also has a projector, and it has a near IR camera. So again, one camera is like a regular camera, visible spectrum. One is near IR camera, and then there's a light source, like a slide projector, that's constantly projecting a static pattern. And I'll post some videos online so you can take a look at it. But that's just stage 1 of how do you use this device to get depth using stereo. And stage 2 is critical, because you have to take that raw depth map, convert that into body parts, an intermediate representation, and then finally use that to infer the pose. And this is a relatively complex operation. It seems magical. It's happening, I believe, 60 times per second. But there's some really interesting things going on, and Dan will describe in his lecture in a few weeks on how this works. And once you know how it works and how easy it is to implement now on some of the libraries, you'll realize these ideas can be implemented in so many levels. Some groups, for example, have Kinect and have started creating And so if you actually look at Kinect, you in fact have as I said, a slide projector that's projecting seemingly random dots, but that are highly calibrated. And the camera is using these random dots and doing a simple match to actually do triangulation and estimate depth. And we'll go through the Kinect architecture in great detail. Okay, next slide. Okay, and as I said, it's being used not just for gaming. As you'll see, actually, that most of the devices come out for somewhat narrow applications like gaming, because it's much easier to penetrate. Except the market is already validated. As long as you create a new human-computer interaction, you can distribute that, and often verticals take longer. Verticals are smaller, and it takes longer for cost to come down. So there's a company called Matterport, and if you can open the browser again, I'm sorry. So this movie, this company, so it's a little new startup, and what they did, they just took the Kinect, which is a device that looked like this, and instead of keeping it static and interacting with it, they said, why don't we just lift it and start moving it to create 3D maps of the rooms, and they're providing it as a service. So very low cost 3D maps using a $150 device. They can create very detailed maps using such a mechanism. You can do texture mapping to hide some of the defects in capture geometry. You'll still see some artifacts along strong edges, but it's only going to get better and better as the devices improve. Yeah, because remember there's an RGB camera also. So you're also taking in the same shot, same frame, a regular 2D photo. What about something like a Litro? What is it exactly? So if you take a Litro, which is one of my favorite technologies out there, and I would say probably the first example of computational photography being available for consumers, is a camera that captures not just a 2D image, but a 4-dimensional image, so-called light field, where in a traditional 2D image, energy is focused on a sensor, and when it's focused, you get a sharp image. But instead of just capturing all the light through the lens on a single point, you would use the lens array is placed with respect to the sensor so that you're capturing not just the 2D image, but the radiance or energy of the rays along various directions. So you have XY, which is the 2 dimensions, and you also have the azimuth and elevation of the incoming light. So they're the 4 dimensions. So there's no time. It's 4 geometric dimensions. So it gets very confusing, right? I mean, try explaining to your grandma that the appearance of the world is not 2D, not 3D, but actually 4D. Right? But maybe your grandma has a PhD, and she'll say, of course. Don't you know about string theory? It's 11D, not 4D. And, but as I said, in addition to the 4 dimension, you have time and wavelength and polarization and so on. Nevertheless, from a geometric point, all the information that can be in a scene is actually represented in this 4 dimension. So wavefront is encoded in this 4 dimension as well. So this was actually presented by Lippmann in 1908, fundamental idea. And then Professor Ted Adelson, right here at MIT, wrote a seminal paper in 1992 where he called it planoptic sampling, planoptic imaging. And then Renning, a student at Stanford, as part of his thesis, built, I would say, the first practical device to sample. And then we'll go into detail in the class of how this is built and its architecture and what are the challenges. But you can start with a 16 megapixel image and then digitally refocus it. Isn't that cool? I felt completely in love. I mean, I knew about this idea, but when you saw these results for the first time in 2005, all of us in the field were highly, highly impressed. But of course, we can do better than Stanford, right? We're here in Boston. So I and my colleague Amit Agrawal, who's sitting in the back, we came up with a new method using not lens slit arrays, but using printed masks. Taking an idea from communications, where you don't use time division multiplexing for communication, but code division multiplexing, CDMA. We use the same idea for capturing light. That allows us to create these types of interfaces. So what you're going to do in the class is use a software that also comes from Stanford, built by Andrew Adams, who was actually a postdoc here at MIT for some time. So Stanford folks also end up being here at MIT. And he wrote this very nice app to actually take this light-filled pictures and then in software show you all the abilities of digitally refocusing it, changing the aperture, and so on. And changing the shape of the aperture as well. It's not necessarily a circular aperture. And you can think of a light field as basically an array of images created with an array of virtual cameras. So in a light row, I believe it's of the order of 100 pictures. About 100 cameras, 100 virtual cameras are built into this device because you have microlenses array. Microlens array, where under every microlens you have about 100 lenses. We'll go through the theory and math and how to build applications on top. And let me skip through this because we'll go into this much detail. And as I said, it's a concept of virtual cameras. But beyond digital refocusing that you may have seen, you can do some interesting things. You can look through foliage. So you saw this picture before. So you're looking at this array of cameras. Array of cameras is another way to capture light, by the way. And it allows you to, from a single camera, might look like leaves and foliage, but using digital refocusing, you can see. And if you're interested, you can do this as one of your apps in your class. So if I'm looking through the foliage, instead of having an array of cameras, I can just take a video, record that, and then from the sequence of pictures, I might be able to see through some sparse occlusion. All right. Some other things we'll see are beyond visible spectrum. I don't know if we have a thermal IR camera here. Might have some. We'll look at them during the break. And thermal cameras are interesting because, as I said, they used to cost quite a bit. Beyond a certain resolution, there is export control. You can't even take them in your bag on a flight. Some people do anyway. But below a certain resolution, I believe 120 by 120, actually they are not export control right now. But using thermal IR, you can look at the black body radiation. This is my favorite game of cricket, where you have to make very close calls on whether a ball is hitting the bat of the batter or the legs or the pads of the batter. And typically this was done just by listening to the sound, by the referee. But now using thermal IR, you can actually figure out by the heat signature that's left for several additional frames whether the ball hit the bat or this can change fortunes of countries. So this is very, very important stuff. So we have thermal IR cameras. You can play with them. You can buy low-resolution thermal IR cameras from Home Depot. And as I said, right now, they're not available in very broad consumer devices, but they will have every cool camera technology will be available in phones or gaming platforms or scientific platforms and so on. So we'll be ahead of the game and also try to use thermal IR cameras in some of your applications. Then there is time of flight. We have a bunch of time of flight cameras. Or before that, we also have the Leap Motion, which is a $70 device. And actually, I did a project in 2003 called Multi-Flash Camera. And we'll go into detail in a second of how you can use multiple light sources, not a single light source, and flicker between them to get contours of shapes. And Leap is actually using a very similar idea. It has 3 LEDs and 2 cameras. And it's turning the LEDs in interesting sequence and taking a picture with these 2 cameras and doing analysis of shadows as one light turns on and the other light turns off. I think it's available for about $70. You can buy it online. We'll buy some more, so you can play with it. And then coming to time of flight, we saw this example of a camera that can create movies of light in motion, virtual movies at 1 trillion frames per second. But that cost $1 million. We had to go to optics labs and build it. Well, in mid-90s, there was an Israeli company called 3DV that started selling cameras that uses time of flight. So you send light from the camera, it starts reflecting back. Points that are closer, like the nose, will have an energy front that's ahead of the light that's reflected from the forehead, for example. And the camera is fast enough to see the delay between what's coming from the nose and what's coming from the forehead. This thing used to cost, I forget, about $30,000, $40,000 when they came out. The technology has improved dramatically. Back then, they thought they would use it for virtual studios, where you can insert graphics. Not just a weatherman, where you stand in front of a blue screen or a green screen, and the green screen is replaced by the map. But you can put virtual objects anywhere you want. And it turned out this was not a very big market for them, and they didn't do so well. But eventually they sold to Microsoft, and that team now is working on Kinect-related projects. And we'll, in later classes, we'll look at the math behind this time of flight cameras. And as I said, the new Kinect, I think it's called Kinect 1. Is that right? Which is so confusing. Should we call Kinect 2? And I believe it will come out at Christmas. So we don't have those prototypes, but we do have collaboration with that group, and we might get something by early November. Nevertheless, there are other companies, as I said, Soft Kinetic and Mesa and PMD, with whom we have a lot of prototypes, and you can build some demos on top of that as well. And so we'll go through all the principles of how this works, modulation and demodulation. There are good software libraries. An interesting point to make here is that often you can use the libraries that are provided by the vendor, where you just make one call, give me the map, and go ahead and use that. But if you have to be ahead of the curve, sometimes you have to go and look at the raw data. Much like in photography, if you want to do something interesting with your photo, you cannot just take the JPEG compressed image. You have to look at the raw data. It's also true for all these devices. They're pretty easy to use because the SDKs are available, but to do something unique and magical, you look at the raw data, try to understand the physics principles behind it, and then you can exploit and do something really interesting. All right, so let me wrap up here and hand it over to John, and he will talk a little bit about cameras and where they're going, and I'll come back later on and talk about not just devices that are out there like Kinect and glass and deep motion and time of flight sensors, but also this concept of how we can create attachments to cameras and see some really unique applications. So this particular one is called Netra, which came from a group. And the idea is that you attach it to your phone, or older phone. And you look through this, click on a few buttons, basically play a game, and when it's aligned, you hit calculate, and it gives you a prescription for your eyeglasses. Nearsightedness, farsightedness. That's all based on the notion that the resolution of the screen is improving dramatically. The pixel pitch on your phones is down to about 17 micrometers when you have 450 dpi, dots per inch pixel, per inch. And you can do some amazing that allows you to build attachments that mate with your phone, I guess, optically, mechanically, electronically, possibly chemically, and so on, to really transform the functionality of it. So let me hand it over to John, and while we're switching over, any questions on kind of a quick walkthrough of some of the devices that we'll play with in the semester? Of course, you'll be using a standard Android phone as well to build apps, and that will be part of some of the homeworks. But I hope you will think of projects that are slightly ahead of the curve, and think about not pure software solutions, but solutions that might involve interesting software and hardware.
John Werner, I'm the project innovator in the camera culture group at MIT. As you can get a sense, Ramesh is a great guy to work with. There are 30 of us in the group. Dan, Nikhil, Daniel are some of the other members. The 30 of us can be a great resource for you guys as you think about the different labs you do and the projects you do throughout the year. So MIT was founded in Oh, I think so. The Canadian speaks up. Yeah, I think it'll work. So MIT was founded in 1861 by Copley Square, and it was known as Boston Tech. And they wanted to do hands-on learning and work with industry. And it was in cramped quarters. And right next to Copley Square, they started filling in the Back Bay area. It was around 1860. And it was a really successful real estate play. I don't know if any of you have been to Back Bay. So the folks who had done well over in Boston over there looked at the land by this train station, right where we are now, and said, hey, let's do the same thing. So they planned to put a lot of real estate in here, people's homes, but they realized the economy was tanking, it didn't work. And there was a camera guy named George Eastman who had done incredibly well. He had been kind of the guy behind film. He anonymously bought this 1 mile strip of land right here. And in 1916, Boston Tech moved across the river, came to Cambridge, and hence MIT as we know it. And one of the main things that happened when MIT moved here was the building of the McLaren buildings, the Infinite Corridor, Killian Court. Who's been there? Okay. And there were a lot of technical schools around the country, but this one, the different disciplines worked with one another. They connected with one another, and there was incredible innovation in the 1900s. And part of what I want to help facilitate is to celebrate the talent in this room. And the camera, the camera phone's come a long way. It was just a few feet from here that Watson connected with Alexander Graham Bell in downtown Boston for the first time, a 2 mile call. And I think some of the stuff that's happening in the near future can be as exciting as far as we've come since that moment. So I want to take a few moments to say something about who's in the room. So I asked you midday to kind of fill out stuff about you. So, sitting in these seats right here, we have someone who does radar systems, a civil engineer, folks from the media lab, someone who's a jack of all trades. They listed a bunch of different things you can do. Biophysics, he's actually in Zurich. I'm going to come to that in a second. Someone whose grandfather had a big patent in film. Hydrodynamics lab, someone who knows a lot about surveillance. So we have talent in this room. Ask you guys to email a few things that you're excited about the hardware that we're working with and how you might apply it. And so here's a word cloud on it. And you know, as you guys know, the bigger words are the words that get repeated. But I think this shows the diversity. And imagine how these things can combine throughout this semester. I also asked you to think about the ultimate camera, because as we think about hardware getting cheaper and the future of cameras being a lot in ingenuity around software, thinking about what could be and how to get there is something that we're going to do a lot in this class. And so just to highlight a few of what you said. An immersive world, a camera that can document everything around you. Ramesh kind of talked a little bit about that. Aware of the environment it is. That means the camera's smart. So it's not just something that opens and closes, but it you know, takes information in. A number of you said, I want a camera that is directly connected to my brain, and I can activate it with my brain, or it can read my brain, or it can scan my brain. And a lot of you have some ideas on that, and I know we have some medical people in the room. Capture what produces an emotional response. So that kind of connects with the brain, but there's some other things. Take good pictures in the dark. There's RAW and a lot of post-production going on, post-processing, but maybe through combinations of the people in here, we can come up with some new standards. Things our eyes cannot perceive alone. Many of you submitted things like, I want my camera to do more than just see different colors, and I think you guys can come up with things on that. I also, throughout the New York Times article, there are 10,000 Google Glass out there, 2,000 with programmers, 8,000 with explorers, and the press, you know, are slowly, you know, writing about it after a few weeks with it. And you know, I think this was a balanced article. You guys had a lot of interesting points, saying, you know, why'd they go for style and not just functionality? You know, thinking about how this is going to change society and so on. So, you know, thank you for reading this, and we're going to have a lot of discussions on the kind of work that you guys look at. We also asked you to think of if you had glass, and we have 10 pairs, and we want to get them to you and to use them. You know, create glass where if you wiggle your nose or blink, you can activate it with someone's idea. Have glass document how I move, someone else said, you know, instead of looking out, have the camera looking into the eye, and maybe there's predictive analytics that can do things around health. Someone here, and we have a bunch of you who are architects, said, I want glass that if I walk into a room, I can document the whole room, and it's suddenly sketched. And if I want to increase the lighting, or I want data on things, you know, related to thermal or other things, that I can pull that in, and how that would change, you know, that work. Some of you, 2 of you said, you know, I do field work, and you know, right now, you know, these you know, people notice them when you're wearing them, but you know, there are ways that this can help with field work around the world. Someone said, I want to put it on my dog, you know, just run loose and, you know, see what they do. So there's all sorts of practical and fun and interesting things, and it's the combination of the talent in here that'll come up with it. And then one of you said, you know, I'm going to swap out the processing power, and you know, let's do it, bring it on. So a little bit about our community. So A is where we are. We're in Boston. We're in this room. B, right now in Zurich, about 30 folks, and folks in this class are there right now. Google is hosting a meeting to talk about, you know, how to program for this device. And when we said that an element of our class, computational camera, was going to be around this, Tim Jordan and Thad, who was at the Media Lab for years, were ecstatic. They said they know of no other class in the world right now that's teaching programming apps for glass. And they are so excited about what we can come up with. And Mooney is part of our group, and Adam, who's a biophysicist from Harvard, is enrolled in this class too. He's in the workshop right now. The other thing about this group is that we have the folks right up here at Skoltech, and I asked them to fill out some surveys and to get to know them. You know, 2 from Pakistan, biology major, studio photographer, 3rd place in Microsoft Connect, have gotten 500,000 downloads. So as you guys combine and think about projects you want to work on, and Ramesh mentioned this, you can do a call out to these guys, or they can do a call out to you and say, hey, let's work together. And given the different time zones, we could be really efficient over the 12 weeks and work 24 hours. I'm not saying that that's recommended or suggested, but you could. And I think recognizing that there's talent over there. The other thing is, yesterday we opened up and said, who wants to take this class online? And within an hour, we had 150 people signed up. As of today, 300 people are signed up right now. Now, I haven't looked at the numbers, but I quickly shot out an email to the people who are online right now outside of School Tech and outside of this room and say, hey, tell me a little bit about you. And we have a futurist, we have a Fulbright scholar, someone who won Young Innovator of the Year in India. We have diversity, and then I think as we think about the stuff we want to do, tapping into this talent can be really helpful. So for this segment, I just wanted to say, you guys are as important as what we have to tell you, and we want to help support you as you think about the different projects. If you want to get to people that can help you, part of my role is going to be have an external focus on that. So turn it to Rohan.
Right. And the lab is our world. So think about if you build an app and it requires users to get started, we have to help each other out. And we have to all download those apps and start collecting pictures and provide it. I mean, if you tell you, for startup, the biggest challenge you have is users. Have this large community in the room as well as online. I think we can be nice to each other and for testers, we can all But let's have this army of people.
All right, everyone stand up. Let's shake our legs a little bit. All right, I want you to put your hands up in the air, make a really silly face. I'm going to take a picture. We're going to put it on Google Plus. Okay, Glass. Take a picture. Beautiful, beautiful. I'll post that up later. All right, I'm going to talk to you a little bit about Glass today, a little bit about me. I work a lot in the startup community around Kendall Square. So Techstar, Startup Institute, Lean Startup Machine Innovation Lab at Harvard. Very well plugged in there, and I'm currently prototyping some hardware to interact with wearable tech like Glass. So let's talk about Glass right now. Google Glass is Google's attempt to change your perspective. Okay? It's Google's attempt to actually take you away from the virtual world and bring you back into the real world. However ironic it might seem, by bringing the lens and the screen closer to your face, they believe that they can take you out of your smartphone. Essentially bridge the gap between the virtual and the real world. So, here's a little graphic. They have two main principles with Google Glass. One, it's there when you need it, and it's out of your way when you don't. And second, it brings you back into the real world. They have this really cool graphic right here. Talking about how people interact at concerts. 1970s, we got peace signs. 2000s, we got cameras. 2012, we have iPads up at concerts, right? In 2013, our hands are finally free again. Why? Because the device is part of our body. And that's what they're trying to do with Google Glass. Let's talk about Glass itself. We have two diagrams here. At the top, I'll talk about the hardware. And hopefully in the break, you guys will be able to interact. We have about 5 pairs to interact with here. On the back is a battery. The reason why they put it on the back is to counterbalance all the weight on the front. So you see the computer, the camera, obviously the prism at the front. That's a lot of weight to have on the bridge of your nose. So they've actually placed the battery at the back to tuck it away and counterbalance sort of like a lever. On the side, we have a full touch panel. So this white part right here, this part on the side right here is actually full touch. So I can swipe left and right to interact with Glass or swipe down. And you can do other things as well as soon as they open up. There is a microphone, obviously what I just did took a picture of you guys via voice. A camera and the prism, which is the visual overlay. And so when you guys get to try this on, how many of you have tried this on already? When you guys get to try it on, it's actually incredible what you see. Incredible what you see. You see a screen, but it's actually slightly translucent. And Glass knows how to modulate the light to make it brighter if you're outside and darker if you're inside. So what you can actually do is augment what you see. What Google has done is they put the prism slightly above your center of vision. So it's actually in your periphery. To see it and to notice it, you have to look up into it. Okay? And the point of that is that, again, they don't want it to be in your face all the time. It should be something that happen chance you get an email notification, you see it at the top, you can ignore it. Rather than the buzz of your phone, it takes you away from the real world from your earphone. My favorite part of glass by far is the speaker. The speaker. If you ask me why is that your favorite part? Well, inside there's what looks like a button. It's not a button. Don't press it. It says the glass logo on it. It looks like it's a button. What it is, it's a bone conduction speaker. Bone conduction speaker. So what that does is it converts electrical energy into vibrations, conducts the sound through your bones right behind your ears. So that way you can keep your ear free. So it's actually it's very, very interesting. So you keep this sound private to you. People can still barely hear the noise, but it's not the same level. And more importantly, you keep your ears open. There's no headphones blocking it. You won't be able to, you've seen the Bluetooth headsets where they're plugged into your ears. Right? So that's what they've done to get around that. So what else? The gyroscope, accelerometer, we've seen that in your phones. Compass, orientation, so you know where you're going. Google Glass in its alpha version right now has GPS navigation built in. And the best application I found for it is riding my bike and being able to tell where to go. It's absolutely incredible how well it works. And it has Bluetooth, Wi-Fi, 5 megapixel camera, and 14 gigabytes. And that's all housed in a custom chip coming right in this. Ramesh talked about the projector and the prism and how it focuses the light in. You'll see it. I can't really explain it until you actually see it. Hopefully you get a chance to put it on later today. So how do you interact with class? Right now there's two ways to interact with class. One is with voice. So I just did that in front of you. Okay, Glass, take a picture. There's also record a video, get directions, do a video call. You can actually do a Google Hangout through Glass. And you can interact with the apps on Glass. So you can say things like read aloud the instructions. And I'll show you some apps later that do that. And then the second way is by swiping. So Glass looks like this when you look through it. Okay? There's cards aligned horizontally, and it's called your timeline. So to the left are things that are happening now. So this is Google's implementation of Google Now. How many of you are familiar with Google Now? Yeah? How many of you have an Android phone with Google Now on it? Okay, so Google Now is Google's really creepy way to give contextual awareness to what you're doing. Okay? It's really creepy until you start using it for a while and you find it very convenient. So it's one of those controversial things at first, and now everyone really loves it. What it does is it scrapes all the Google services you use and gives you information as you need it. For example, if I book a flight, it shows up in my email. Google knows that I have a flight receipt in my email, and the day of my flight, it'll say, hey, your flight's on time, here's the gate you have to go to, and here's when you're landing.
Unless our fans are wise.
Yeah. Better? Okay, good. Main card is the current cards. That's what you're on right now. So you're basically swiping through this timeline of cards. The main screen is actually the time, and at the bottom you say, OK, Glass. That's the only screen where you can interact with Glass OS and say things like take a picture and record a video. And to the right are things that have happened in the past. So what you can do is you can pin cards where you can see things that you've done before. So if I swipe to the right, I would see the picture we just took. I would see the call that I placed yesterday. And I would see a text message that I also texted. So how do you develop for the timeline? How do you develop for Glass right now? Well, I will tell you first to start that the way you develop for Glass right now is different from how you're going to develop for it in about 2 months. Okay? And so I'm going to tell you both ways, and I'll tell you which way I recommend. So this is the way you develop for it officially. There is what's called Glassware, which is the software you develop for Glass. It is basically a web app. Okay? And it interacts with HTTP, goes through Google's big wall, and then Google syncs it down to Glass. So what does that mean? Well, we have limitations. There's 10-minute location updates because Google doesn't want to sync this all the way down all the time because the battery will die. There's no live access, no microphone or camera. There's no cellular access. There's no hardware access, right? It's a web app. It's essentially a notification center, and that's how you interact with it officially right now. Cards synchronize themselves down to the device, so it really is just a notification center right now. There are some apps that you can use, but again, it's up to Google when you receive it. Interaction is delayed. It's not necessarily real time. That's the official way. So, as of 3 weeks ago, I think 4 weeks ago now, Google posted on their Google Plus saying, we don't want you to do it this way because this is really limited. We want you to build really cool apps. So I want you to develop for Glass as if you would develop for Android. For Glass as if you would develop for Android. And here's how you root your device, and here's how you put an APK file on your device. Now it's going to void your warranty, but here's how you do it. A very early indication, and we have confirmation from the guys working at Glass that this is the way that you should do it, and it's going to be very, very similar to be interacting with Android. That's good news, right? That gives you access to the hardware, the microphone, the camera. You should be able to connect Bluetooth to any external peripherals, like Arduino, and you should be able to create augmented reality. Let's go really quickly through some exemplary glassware. This is one of the first apps that was ever released for Google Glass. It's NavCook, and this is using the official way to interact with Google Glass. Basically, you choose a recipe, it'll sync down a card for you and show you the directions step by step. You can swipe left and right or say next step, and it will read it out loud. So the idea is that at the kitchen, you can be hands-free and interact with this information as you need it. This one's really cool. So obviously, let's go through the not cool one. This Glassogram, of course. If you have a camera, we're going to make Instagram for it. First thing. This is about I think this is the second or third app that was released. You take a picture, you add a filter, you post it. What's more interesting is this picture on the left here. This is a video of somebody using an app that they developed called Winky. Winky was developed unofficially, before Google even said to develop it. What happened was, some developer got interested, rooted their device, and peered into the root OS code, root Android OS code. They found two parameters in there: blink gesture on, blink gesture off. People had never mentioned anything like that, but if you look inside the glass, there's a tiny, tiny sensor inside. What it can do is it can detect your gaze and your blink. So what somebody did was they turned it on. They said, I'm going to turn it on and I'm going to put it into an app. And what they were able to do in that video is take a picture by winking. Now I think there's a lot more creative things you could do with a blink or gaze detection sensor. So that's what we want to encourage you to do. But that was big news, and I'm sure there's a lot more coming. This is one of the newer apps, probably one of the more fun apps. I have this on my device right now. It's called Glass Battle. It's Battleship. You can play it with friends. And again, it's using the official Google means of developing apps. The reason why is because Glass Battle is really easy to use using the official means, because it's a turn-by-turn based game. So essentially, you say B5, it'll place a marker down there and notify the user if there's a hit. So cool application of the sort of sync down notification. This recently came out, and it's actually being explored by Tesla themselves. An independent developer who worked at Tesla for a while got access to the Tesla API and was able to peer into the car's information. Another really cool application. What you can do with this app, if you have a Tesla vehicle, which I don't, is you can see your mileage, you can see how much gas you have, or how much electricity you have left, you can see the temperature, and you can do things like lock your car or unlock your car probably, start your engine. So again, pretty interesting applications of it in a situation where you would have to be hands-free.
That's critical. That the world of APIs is really transforming.
Absolutely.
And you never know which next device is going to work. Actually, they all should.
Right. I mean, the reason why we have so many of you, what APIs you've worked with before, or you're interested in working with, developing stuff on Glass and on all these other devices, peer into them. The applications that a lot of people are interested in these days are hands-free applications. So pilots, referees, surgeons, those kinds of people who have to be hands-free.
Glass for the dog.
Right, or Glass for the dog, also useful. So what's next? Google Glass SDK will be released within a few months. That gives you access to all hardware features. Developers are encouraged now to develop for Android 4.4. I've tested it with more than that, so feel free to explore the limits of your Google Glass. You're going to have to be a little bit careful in how you develop for it, though, because how you currently program Android is with touch, right? You have to touch a tab or touch a button. And obviously, you can't really touch on this device besides giving it a swipe to. You have to be creative in how you interact with it. Using the accelerometer, using just a swipe gesture, we're speaking about. And the last thing is they provided rootkits and hardware. Now again, this is unofficial, it voids your warranty, and we'll work with you guys on it so that you can actually do the real-time action. So, what's happened in the last couple of weeks? Google Glass owners will get their first App Store in 2014. If I were to hazard a guess, it's going to be mid-2014. That means Google's putting a lot of money into developing the entire architecture ready for you to distribute your Glass app. Right now, you can distribute your app as an APK file, or you can distribute it as a web service using the official means, and we'll give you instructions on how to do that. But what we want to do is make sure that your guys' apps are the first apps to appear in this store. Okay? That's guaranteed downloads, guaranteed publicity. There's nobody else who has this many Google Glass pairs here for you guys to do. This could be a $3 billion per year business. Obviously, it's still out there to see what the broad consumer adoption will be. But people are willing to pay $1,500 for this device right now. They have this early adopter syndrome. We'll see what happens when the full consumer device comes out. We get a much lower price point. And actually, there have been now a couple live surgeries done with Google. Now, why is that useful besides it being cool for you to see surgery? Well, it's useful because what they did was they did a hangout, a Google Hangout, with other experts around the country. So they had, in this case, it was a heart surgery. They had heart surgeons from Canada join the hangout and advise the surgeon on different things that they've seen before and they've done before, but couldn't fly down to do this. So, really interesting application for communication as well. Related wearables. So this is honestly where things are going right now. It remains to be seen if people are going to catch on. Apple's iWatch is all but confirmed. Everyone knows there's about 200 people working on the device right now, and it's rumored to be releasing in 2014. The Recon Jet Glass Up, there's actually 3 more. There's space glasses. There's another one called Glassware X. They all do essentially what Google Glass is trying to do, but for different applications. Recon Jet is for sports. Yeah. So this is interesting. So this is actually a life locking device.
No brand.
No brand. It's $30, and essentially what you can do is you just tap into the camera and record whatever you want. It's a little bit better looking maybe than glass. Maybe not as smooth. Asymmetrical, right?
And it has a camera in the front. It has a camera in the front, right in the center. Balanced. It has MP3 player. It has audio. It has, I believe it has SD card, so you can record continuously.
$30. Of course, no overset, no overhead display, and that's I think where the big costs come into play. But if you wanted to, dog is looking at, that might be good. The Baidu Eye. So Baidu is essentially the Google of China, and they are now sort of helping develop. So wearing it in this video footage. And Intel is also working on it. Intel's working on their own, which is very interesting. Intel's partnering with other companies. It's also been confirmed to be working on one as well. This one is Glass Up. This is a startup's attempt at making a better looking version of Google Glass. Remains to be seen what you think. It works through projection as well, but instead of a prism, there's a slightly different film as part of the lens itself. You can see it right here. Light red version right there. It's monocolor, but their idea is that instead of putting prism, we can focus anywhere. Let's put it as a flat layer, and that way we can decrease the size of the electronics. The fact that the prism has to be big is a big constraint. Yeah, Samsung's watch came out yesterday, right? So you saw that come out. It's a beautiful watch. There's a camera for this strap. Incredible device. Definitely check it out. It's supposed to be $300, I think. So it's a little on the pricey end.
The whole team is.
Oh, really? Very, very good. So if
Nickel 9 right here, there is internship.
I worked there last.
Yeah. Definitely check out those videos right now. People are reviewing them. A lot of early adopters. All the Samsung Galaxy devices to start. Minimalist version of Android.
How much can you say about the watch?
But not what they what.
They kept you down as well.
And one, yes.
So what's your take on us versus watch?
I think the watch is probably like an intermediate. People might take a bit more time to adopt it, have fun.
I mean, the people like me who don't wear a watch, start wearing a watch. How many people here wear a watch? So I would say less than 30%. And how many fraction of people wear glasses? Right? So it's an interesting
statistics of what people are doing.
It's sort of ebb and flowing, right? You don't really know. First, when glasses first started, polarized and it was weird, and it became acceptable, and then contact lenses came out. And so you see this ebb and flow of societal sort of acceptance of these devices, and we see that as one of the biggest factors preventing people from putting these things. Hopefully, we can invent some really cool applications. Convince yourself that this is early, but it's getting there. I'll believe that it's inevitable. On us all the time. Yeah.
All of these other.
Right. One has a lot of startups do this, right? Because they don't have the manpower to develop it on their own, but even Google is doing it, right? It remains to be seen. I mean, I think we all have a good guess of which one is going to be probably adopted. It's a mixture of price point, convenience, what it looks like, and connectivity with other peripherals that you're used to. So it needs to be seen what they're going to do. Untitled had a very successful crowdsourcing as well. Called Space Glasses. They've actually, let me see if I can pull it up for you guys really quickly. They've essentially mounted a Kinect onto a pair of glasses. And what they're able to do with this
where's the
sleek, huh? Because they have the Kinect stereo camera capabilities, they can actually make things with depth. So their idea is full augmented reality. Let's put virtual objects out in the real world where you can interact with. Now, there's no haptic feedback or anything like that, but they think this is where things are going. Their biggest goal is to get the sensor smaller. So you'll see this at the end. There's some creepy face recognition built in as well.
Because you guys have glasses, decided they don't want to touch
Glasses. Google has formally announced that they don't want to allow any apps. See if that means anything. Sorry. That just for the government appeal, because right there. Privacy. So at the end of this, you'll see a little demo. I'll let this play. We'll wrap up here. But this is where things are going. We're excited to work with you guys and see what we can build. I'm building hardware stuff for it right now. And if you would like to talk to me about anything, let me know. If I can't answer the question, we have people like Google that can. So this is their end goal. So, any questions about Glass? Yeah.
Are they gonna? Is the SDK currently hardware locked to the product, or is it possible?
So the SDK is not officially released. Okay. So right now you have the Mirror API, which is available, and I can tell you that you won't be able to test unless you have a device. So what we're going to do is we're going to try and design office hours and time when I'll come in, and you can test on the device itself. But the other one, otherwise you're just going to be developing for Android and we'll toss it on glasses.
Fragmentation is so big.
Seems like they will be. I mean, they took these first steps to make their own device. It's not tied to any manufacturer. All these chipsets are completely separate. Graphics board, that was custom built, and business differences. So we'll see what they end up doing, right? Eventually, you have to bring the price down and bring in. Yeah, so you can. So I have not done this yet. What I've been doing with my hardware is interacting with it. But we just talked to Timothy yesterday, who said that you should be able to just connect via Bluetooth directly to the device. Interact with it. So Glass actually has Wi-Fi on board, and when you're not using Wi-Fi, it connects via Bluetooth and tethers to your phone. So you always have internet access.
And Timothy was so excited about this class and head up office hours.
Top of legal.
He's in Mountain View. He's in Zurich right now leading the training. university.
What else? Any other questions? Yeah.
Right. Actually really quite distracting. So any thoughts about that kind of happens?
Sure. So there's a couple of social problems that people have. One is that they feel like people have pressure on them. As soon as you put a camera up, right, people shy away. So having a camera always up makes people feel a little bit uncomfortable. So Google is working on technology to allow you to recognize when the camera's recording and locking that down. Later, we won't know. As far as what you said, so in terms of, repeat what you meant.
That's one right now.
You would be distracted.
You're not actually looking, even though you might listen to what I'm saying.
Right.
Because of that non-eye contact, it's really distracting. It's like you don't care. There's social problems. I wonder if either actually.
From what I know, no. I do notice that same problem. It's in your periphery, right? So to look at you have to look up. It doesn't make noises when you get an email. Those kind of things are distracting. I think it's the same social problems that we have now where everyone's on their phone all the time and completely oblivious to everything around them. We'll see how this helps them act. Yeah.
70% of the other.
Oh, very cool. I think it's
Yeah. Just sort of diagnosing it like this.
So again, the professional applications to me are the most interesting. Those are people who don't really care about what they look like, and so you can sort of take the social assumptions away. That they can get this information that they really, really want.
Guys, 10:48. Let's do a break now till 10:55. Feel free to talk to any of us if you want to try some of the devices. We have a lot more to do. Share, get to know one another.
I'm not sure if have a name tag with the name, but 3 words that
That's really good to hear. It's really fun. That's my only device. It's a good one to know. Right. Right. So that's it. We're trying to I know. All right. Like, oh, that's really cool. No. No, not yet. I haven't.
I'm interested in that too.
Then I'll- It'd be nice to have some additional. Have you played it? Yeah. Yeah. I mix up when you don't need Get it. Do you wear glasses? So here's that makes sense.
Yeah.
Swiping down is like the back one. Like higher level. The main page you can say yes.
And it's always in the I just forgot.
Anyone know what
Oh, I'm sorry, I have it. I was like, where's that? All right, so any guesses on what that is?
It is a laptop. It was called the Luggable when it first came out. 17 pounds. It has the same battery that a golf cart has. This was Apple's first computer that you didn't have to plug into a wall. And it was totally ridiculed. It was $7,000, and it might as well sunk into the bottom of the ocean. And people thought like Apple was dead. And obviously, yes, Apple's dead. So I think I'm real excited that there are not a lot of apps for some of the devices that we're working with. And you guys can come up with things. And I was just talking to so, you know, when you think of skiing, you get on two things, go down, or snowboarding. Sports changed tremendously because of the technology. Original skis, you would put like fur of an animal on the bottom of wood. Now it's composite everything. And tennis, the same way. John McEnroe dominated, and he kind of left the sport. If it had stayed wood, maybe he would have dominated for another decade. And you were just saying, well, what if soccer players all had these devices, and the vector of that sport could change because technology is woven in. I know at the Olympics, well, I'm not going to go there. I think what you guys do can make a real impact on some of this hardware. And VisiCalc, in 6 years, sold 0.7 million units of their software. for the Apple IIe. And some would argue that the Apple IIe wouldn't have gotten the kind of escape velocity it did versus the Atari and the Commodore, some of the other computers, if that application hadn't come out. And at Stanford, and Ramesh, we have a great relationship with Stanford, we made some jokes earlier. At Stanford, they've had a tradition of having a class around building apps for the iPhone. And there's one class that's legendary. I think everyone in the class started a company and now they're in the Caribbean or something on yachts or something. But their company in 1 week got 1 million downloads. So VisiCalc, is a game changer with 0.7 million in 6 years. And through the ecosystem, the architecture of the internet, software, we can do things that were unimaginable. And so I want to just reinforce that the talent in this room can combine in that way. So what I'd like to do is just stand up if you'd be interested in taking some of these cameras. This isn't computational photography, it's computational camera. If you would be interested in working with some of the devices that we have on some of these things. And if you want to stand up for more than one, that's fine. And this isn't a definitive list. I just want people to see and connect things with people in here. So education, you want to do something with these devices around education.
And our goal is to see how we can pair you up based on your common interests.
And we're not going to take you to a court of law, if you stand up and you have to do it, right? MOOCs and all sorts of things. There's a lot of these devices can be woven in. And these are not standalone devices. They can work with your smartphone or your camera. All right, shopping, tourism, shopping or commerce. If you'd like to. Okay. Yeah, if you want to rest, for your brain. Okay. Shopping and tourism. Or no, shopping and commerce. I just went shopping in the supermarket, and my wife gave me this list, and I couldn't find anything. And if I had augmented reality, maybe telling me where to go. Okay. Tourism. I mean, you see the Segways, which didn't, go as mainstream as people predicted, but they're used in tourism. These devices have some applications there. Medical and health. Our doctor friend at BU mentioned the surgery that happened. I mean, surgeons, I know a lot of surgeons, they've been using cameras for years. And one of the things I didn't anticipate when I got this was how you're connected to Google+. And suddenly Google+ becomes really a big part of your life. And it's the social networks that the hardware on the can go. Yeah. What's that? Yeah, bring it on.
Well, surgery is one part, but that hardware has the ability to change.
Yeah.
Actually, what is a physician? It's an expert system.
Yeah, well put. And one of the things you may want to think about this in this class is the people in your network that are experts at some of these areas. Maybe they own a trolley company, maybe they're a doctor. Ask them how these kind of devices could be helpful to them, because a lot of those folks are so focused on what they're doing that they don't have time to kind of ideate around these things. And you guys can combine with the talent in this room or some of the people online that we mentioned. Environment-related things. So that seems really popular. Sports. We got one guy over here. Great. Entertainment. Yeah. Okay. So you got a lot of interest in that one. Wearable, just in general, being the future of wearables. Thad, who was up on the screen earlier, made a lot of fun of called Borg and stuff, and look at him now. He's the lead inventor of this device. Robots, quadcopters, 3D related stuff. Anyone interested in that? And so, that's just a small list. This could be infinite. And as you guys take this class and hear what Ramesh is saying and what we're all saying, I think you guys can come up with some great software. And right now, I think the consumer world, knows that something big is about to happen. And I think it's going to be from the talent in here that'll come from. So I turn to our next presenter. I'll give the mic over to you.
And just to get a sense, how many of you have a strong interest in doing programming versus being a collaborator to influence the type of application? Just want to get a sense. How many of you have some or reasonable programming experience? And so it looks like we have only a few people who are not programming experts. So what we would like to do is make sure you're paired up with a team. And as time goes on, we would like to do that. And also folks online said,
could give you very interesting information about what John was talking about. So now we have Gig Nick, and he's going to talk about a couple of devices I earlier described, like Kinect and Leap Function. And Nick has fantastic background in devices and CI and machine learning, and he's also written some open source code that we might use in class. And he's going to show you how some of the software can be used.
Thanks, Ramesh. Hi, I'm Nick Gillian, or Git, as some people, like my friends, like to call me. I'm a postdoc in a group called Responsive Environments at the Media Lab. Ramesh said I do a lot of work with gesture recognition and machine learning and devices. I don't want to spend a lot of my time on devices. That's a big thing I want to say to you today. So things like the Kinect for me have been really important, because before the Kinect came out, I was using, has anyone heard of the Polhemus? I don't know if people have used it. It's a very precise magnetic tracker. It costs about $6,000. And the Kinect gives you about 90% accuracy for, you know, a tenth of the price, right? So the Kinect is really, really important in terms of like what it allows us to do. So I'm not going to talk at all about the hardware, because Ramesh has covered that. So what I'm going to quickly do is give you a quick overview of the Leap, basically what you can do with it, the kind of tools are there for it. How many people here have a Leap? A couple of you, okay. So the first thing I'm going to show you is I'm not going to show you the slick videos that you can see online, because here's one of the things with the Leap. It's improved a lot over the last year since I got the earlier versions. But the kind of system looks like this, right? So this is kind of one of their basic demos. So you probably might have seen something like this. You've got, you know, your fine finger tracking and all this kind of stuff. But if I start to do things like this, you can see that it falls apart in different areas. If I kind of start to do these pinch gestures, some things there are still not working quite as we want them to. But in terms of actually getting this data, there is actually a really nice kind of SDK that you can use to plug into. The SDK basically, it was originally in C++, but now you've got C#, you've got JavaScript, you've got a huge plethora of kind of APIs that you can use depending on what's your favorite language. And from that, you're basically going to get these vector points for each of the fingers and for the hands. There's also now some nice gesture stuff as well, so you can recognize swipes, and you can recognize it as a two-finger swipe up or left or right, or these type of things. But there's one kind of fundamental problem with this at the minute. If I want to orientate it like this or do something else with it, it still doesn't quite work what we need it to. So I have seen a few interesting applications of this. Probably the most interesting one I've seen is actually for medical devices. I don't know if you've seen this yet, but basically in a surgery, the surgeon obviously doesn't want to be touching hardware, so he can basically you know, flick through the medical images and stuff, or look at kind of the x-rays without actually having to kind of descroll and kind of go through those. That's kind of one of the nicest applications. There's a lot of demos online for this, but one of the problems they're looking at is they're basically taking kind of custom desktop applications and trying to plug the Leap into it, which I think is a really bad idea. So I would encourage a lot of you to kind of, if you want to use things like the Leap, to think outside of that and say, well, what is actually not being able to touch anything in free space? What does that kind of afford? And what should I actually play with, rather than trying to just recreate a desktop interaction? So that's basically all I'm going to say about the Leap. There's a lot of videos online that you can watch to kind of check that out. And they have their developer website as well, if you go to the Leap website. For me, the Kinect has made a much bigger impact over the last few years. So I'm going to talk a little bit more about that. So there's, I should say that I use the Kinect a lot. So we have one application in the lab, which basically is a large-scale tracking infrastructure, where we actually have 25 Kinects that are distributed across the Media Lab. And what you're actually seeing here is the real-time location of people walking around the lab. And we're basically taking the data from the Kinects, and hopefully, given the time of the day, we might see a few people walking around here, skeletons and stuff as I talk. So basically, there we go, there's one person and two people. So you can see there's skeletons, right? So basically what we're doing here is we have, 25, 30 Kinects distributed right throughout the building, on top of these like large-scale like infrastructure displays that we have. We're combining that with other sensor data like RFID and Wi-Fi signals from your phone, this kind of stuff, using this probabilistic framework, and we're combining that all together to be able to kind of understand who might be in front of the display and actually track them around the building and do different things. So the Kinect has kind of been really important in this, because what it means is you can now walk up to the screen, and as you'll see in a minute, within 2 seconds kind of automatically calibrate a skeleton to that person, so they can walk up to the screen and kind of use gestures to kind of interact with the screen, even though they're maybe 3 meters away from it, which is kind of really interesting. So you can check this out yourself. It's on a website called ge.media.mit.edu if you want to check it out later. Anyway, let me quickly cover some of the main kind of SDKs that are out there. So in my opinion, there's kind of 4 really good ways of working with the Kinect if you want to actually interface with it. There's obviously the main Microsoft SDK. Then there's OpenNI, which are basically a company that's come out of PrimeSense, which allows you to hook into the Kinect and other devices that PrimeSense sells. You've got Synapse, which is, if you just want the skeleton data to do something else, it's a really good thing to really quickly work with. And then obviously there's this thing in Open Frameworks as well that you can use. So I'm just going to very, very quickly go through the pros and cons of those. Okay, starting with the Microsoft. Well, the nice thing about it is you've got calibration-free skeleton tracking. It works with both standing and seating modes. You get joint orientation as well as the position. And it can track up to kind of 6 users, normally 2 with full skeleton tracking. And it also does some other nice things which are really useful if you want to kind of create these hands-free interactions, which is speech recognition and face tracking. And the best bit, there's some really nice code examples in kind of C++ and C#. Disadvantages, however, it only works in Windows, which is kind of a big tie. It's pretty CPU intensive because the Kinect was originally designed for kind of the GPU unit on the Xbox. So when you port it across to your computer, it bugs the machine pretty much. I've seen the skeleton tracking feel really badly when you're not actually standing in the middle of a room like this playing a computer game. So if you want to use it in like some other kind of infrastructure, I've seen it fall apart very quick. So if you're standing behind this table demonstrating, for example, my skeleton's going to be everywhere. OpenNI, this is the one I personally use the most. So basically, OpenNI is this not-for-profit organization which has really come out of kind of PrimeSense and other people. I don't know, I'm sure many of you have heard of it. Basically, they have a lot of SDKs, APIs, kind of middleware designed for things like the Kinect, depth sensors, etc. Best thing, it is cross-platform, which is a huge advantage. It works with multiple depth sensors, so not just the Kinect. So I'm sure some of you have used some of the other PrimeSense sensors, which maybe give you a better resolution and also work a little bit closer as well. So it works with those as well. It's got some pretty good skeleton tracking, in my opinion. It works nicely. It's calibration-free now, which is awesome. The problems with it are the installation. You know, there's a couple of different things that you have to do. You set them up once, but there are 3 or 4 different layers that you have to go through. The API is really good and huge, but because of that, it takes a little bit of time to actually digest and get your head around it. But in my opinion, it's one of the best ones out there. This is what I would recommend if you do not want to actually jump into the code, you just want to get skeleton data. And this is what I use a lot in my kind of gesture workshops and stuff. So basically, Synapse is an application that uses the OpenNI backend. And a developer has released this. Basically, you can also jump into the code as well. He's released the code. And it basically spits out these tracking information over a network protocol. So another application that you guys write can actually listen to that, which is really useful. So if you just want the joint data and you don't really care about any of the depth information, this is pretty useful. The best thing about it is if you're an OS X, you just download the application and away you go. It's got everything you need. On Windows, you have to install a few drivers. The only disadvantage with it is that, well, the main disadvantage is that the skeleton calibration kind of needs this pose. Which means that if you want to have an interactive application, like I have in the building, where you have like people walking past screens and just want to do a gesture, this will not work. It doesn't really make sense. You have to walk up the screen first, do this for 5 seconds, and it's like, okay, great, and then you walk up. It doesn't really work. But let's, for example, say you wanted to do some home entertainment system or a medical system. To do this, 2 seconds, and then you're like in the surgery for 4 hours, and you don't leave that area. It's not really a bad thing. And to be honest, this calibration does make the skeleton a lot more accurate. So, there's certain trade-offs there. One slight issue is it only works with this Xbox, this Kinect. So this is like the Xbox 360 Kinect. So there's like 3 types at the minute. So it only works with this one, not the Xbox for Windows or the Kinect One. It won't work with those. Finally, if you don't really care about skeleton tracking, but you want to do some cool kind of stuff with the depth map itself, the easiest way, in my opinion, to actually get that is to use this wrapper that Theo Watson has created for open frameworks. I don't know if you know open frameworks. It's kind of like processing. It's a C++ version of that. It's basically like an easy framework to do like graphic drawing and stuff in C++ without spending a lot of time kind of creating the OpenGL backend and stuff. It's kind of cool. It supports multiple connects. It can do some pretty cool things. The main problem with it, though, is that it doesn't give you any skeleton tracking. So if you want to do skeleton tracking, you have to kind of work all this out on your own, which is okay, so that's really quickly going through all of those. I'm going to put these slides up online if you want to kind of delve into those in a bit more detail. But let me actually kind of show you a quick demo to demonstrate this stuff happening. So this is kind of a common setup I use. I basically created this back-end program that I run. It's kind of like a small server that uses OpenNI to talk to the connector. It uses the Knight library to actually do the skeleton tracking stuff. So that's one of those middleware things that OpenNI is. And then it uses this networking protocol called OSC to actually allow this program to actually talk to multiple programs, okay? So the cool thing about this is that I write this program once and then I can actually just spit out the skeleton data for lots of demos like what I'm about to show you. This program itself is just a small application written in open frameworks. And it's using one of the gesture toolkits I've created. So let me quickly show you this. Okay, so the first thing I'm going to do is boot up this backend program. So this is my kind of backend server, which is giving me the depth image. So a little high. So you can see that after a couple of seconds there, as soon as it sees me within one frame, it kind of recognizes that there's a person there in a vehicle, and in a couple of seconds, it then blocks a skeleton to me. So you can see it's got this non-calibration skeleton tracking, which is kind of cool. Okay, so now that that's running, I'm going to show you this other application. So basically, this app is receiving that data over this network connection. Okay, so you can see here, I'm drawing basically, it's kind of hard because I can't see the screen myself, but you can see the main skeleton of the main user, but it can also track up to 10 people. So if other people come in behind me, you can see them walking around as well, and you can grab their skeleton if you need to. You can see I'm getting kind of like the main norm of the person, so I can tell, you know, for example, for one of those screens in our lab, am I actually looking at the screen, or am I facing this way or doing something? And these graphs that you can see in the top corner are basically the XYZ of my hands, right? So if I wave to you, you should be able to see this kind of XYZ.
Yeah.
Okay, cool. All right, so what I'm going to show you is a quick gesture demo. Basically, I set this up so that I'm just inputting this data into my gesture recognition toolkit. I haven't actually trained it to recognize any gestures yet, but I've kind of set up a framework. So when I hit the R key, for example, it gives me a couple of seconds, and then let's say I want to do like a pointing gesture or something. So now it's recording my data. Okay, so that's like gesture 1, okay? So this is called supervised learning. I'm saying like, this is what gesture 1 means. I show it the gesture, okay? This is now gesture 2, whatever that means. And let's say gesture 2 is like I want to stretch like a song. So now it's recording. Okay, so that's my data. I now throw that to a machine learning algorithm, and I train a model. And what's cool is I can now do this prediction. So what you can see is in the bottom left-hand corner of the graph, there should be these two boxes now, right? So hopefully, when I start to do this gesture, you see, oh good, I can see the thing up on that screen, which is useful. The yellow box lights up, right? So it says, you're doing gesture 2. And then if I kind of go over here, you know, blah, 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 that you're doing gesture 1, okay? So what's kind of nice about the toolkit as well is that it recognizes that I'm not actually doing a gesture, which is useful because you're, you know, if you're doing medical surgery or something, in that 4-hour surgery, you're probably only going to do a gesture maybe, you know, 0.001% of the time, right? So you need some way of doing that. I have some nice things I was going to connect up to, but the audio is not working, so I'll just skip over that. But that kind of gives you a very quick demo of kind of what the data looks like. By the way, the data that you're seeing in the top corner, those graphs, there's a small low-pass filter. But apart from that, I haven't really changed it in any way. Okay? And I'm going to put these slides up online.
And the code is available, so
yeah.
if you want to build any app on top of it,
It's completely open source. It's a C++ toolkit. If you look at this website, nickgillian.com, you can access it for free.
Is there that at all, or is it?
So what I'm sending out here over the network is just the skeleton, but I also have a TCP backend that actually sends the depth images and kind of the label image and the RGB image if I need them. But it's a huge amount of data, so in most applications I only really actually use the skeleton.
Right.
But you can access it.
But you have it, and then can it tell the difference between a finger wag and a fist?
No, so that's one of the big differences between this version of the Connect and other versions of the Connect, where you basically have this one, the resolution is like 640 by 40. So even here, with a lot of machine learning, you could kind of pick out the fingers, but at this resolution, it's really hard. In the new version of the Connect 1, they have done a lot of work to kind of recognize like grasp gestures, but still getting that finger detection is hard. I mean, you see, even with the leap, it's hard to get. So, yeah. But you can, with OpenNI, you get the raw depth image, which is really important. So you can do some cool stuff with
some learning.
Yeah.
And Rafael wants to hear about understood in our group. When the new Connect one. Yeah. So maybe you want to say that Connect 1, Connect 2, and what's coming.
So I mean, one of the big differences, they've changed a lot of the backend technology about how this. So I'm sure a lot of you know kind of the story of where the Connect came from in terms of like PrimeSense, etc. When Microsoft got this original version from PrimeSense, they actually completely like tore out the backend pipeline and completely reconfigured it to do all the skeleton tracking. But they still use the same kind of raw technology. The big difference between these Connects, the Xbox 360, the Connect, and now the Connect 1 and later the Connect 2, is that from the Connect 1 onwards, Microsoft completely changed the actual hardware technology itself. So I think they're now using time of flight, right? Whereas this here has got to do with structured light. So the big difference is that with the new sensors, the resolution is much better. So you get a much, I think it's 1024.
And also the depth resolution is claimed to be about 1 millimeter. Distinguish your
So we'll see. That's a big difference in terms of your question about finger tracking. With that type of data, then you can walk a lot more in that direction. But the problem is, because the image is much better, you need a lot more computation to actually work through it. Yeah, so do we need huge GPUs in our computer against GPUs? So I don't know, but it's very exciting, and I really hope they actually make it so that the SDK works on multiple machines and not Windows only, because that would be just bug.
Yeah. Final question. All right, thanks, Nick. And Nick is actually leaving us very soon for some other bright side.
Yeah. This is where you can access these slides.
But you're here for this month.
I'm here for another month.
And then for the other people who can help you.
Yeah. Put this on our site.
Yeah.
So as you can see, what we're doing in the second half, and this is still a fast-forward preview. We'll go into more detail some of these things, and Dan is going to come next. So in the first half, we talked about hardware and some of the optics and sensors, and now we're transitioning into realizing that it's not just about the hardware and clever physics, but also the computation. So we just saw literally a 10-second way of training gestures using simple machine learning tools to use that labeled data to interact with time. And then Dan will also talk about some ideas in computer vision that you can use in addition to that. There'll be full-fledged lectures on all these topics, but I want to give you a flavor of what's possible.
How much time do we have? That's great. So hi everyone. So my name is Dan. Hi everyone. No need to stand up. So here's the deal. 10 minutes of computer vision. So just to be clear, if someone here never done anything in computer vision, or everyone are experts? Oh, I see. Okay. So here's the deal. First of all, don't worry. Okay. And I see that most of you do have some computational background, which is good enough with what we need. And for the next few slides, I'll be talking a little bit about computer vision in general, and specifically what we actually need for this course. Now, before we start, I must add something to this lovely lecture that you gave us earlier. You actually get the depths sensing. Okay, so you have a cool hardware to actually give you the depths. How do you get the scale? Is it simple? Is it trivial? How to actually do that? Now, I have to mention a name here that never came up when everyone here talked about this sensing. His name was Jamie Schuster. A guy from Microsoft Research basically came up with a real-time algorithm that gets this 3D sensing depths, and out of that one, evaluate the location or the position of each one of the joints of the body. Okay, the entire concept they actually use is called random trees learning. And we're going to go over that one, not today, but probably in the next lectures. So the first time I ever heard about actually computer vision was many years ago. People showed me the first row here. They told me, okay, check it out. You have images, and you want to work on images. Do something about it. Like, let's say, denoising, edge extraction, whatever. We call that image processing. Now, the image comes from the real world. And in the real world, we have geometry, and we have the photometry. So if you would like to go from the real world to the image, you need to generate it. Let's call it computer graphics. If you like to take the images, understand what you see, that's the thing we call computer vision. Now, I have to admit that during the years, I hated that diagram. Because in practice, it's not that true to say, okay, here we have 2D, here we have 3D, going from one to another. Now think about the following example. Today we're looking at hyperspectral images, we're looking at MRI images. So we have cubes of data. So now we have our data in our street. R is the real world. So each point in space has some data. Think about DTI images, diffusion thermal imaging. Every point in space, we have much more information. We have a 3D, actually R6 tensors of data. So the data that you actually get today is not just the image RGB. It's much, much, much more. So here's a question. So what is computer vision? Let's try to answer a few questions. So at least in my mind, computer vision is everything that handles visual content. Okay? So what is the difference between visual content and every other content or data or whatever? So for me, it means that every point in space has some correlation to the next one. So we have spatial connection between points. Why is this vision, by the way, so difficult? That's what I'm going to leave for you to answer. Bear in mind the following thing. 40 years ago, something like that, people thought that computer vision is going to be super simple, and computer graphics, that's going to be the hard problem for us to solve. Now, 40 years ago, when people talked about computer vision, they thought about lines, curves, surfaces, maybe, something like that, and that's it. So they thought, okay, that's going to be easy. But today we know it's entirely not true. It's false. So what do you think? Why is computer vision so hard? Sure.
What about how we see?
Actually, we know that great. Think about it. Today, if I give you I know a physical simulation, I know exactly, if you give me the geometry, I can generate you a lovely scenery. I know what it is. Okay, I can generate it. Think about it. Something else is bothering us.
First change from raster image to vector image.
Okay, that's the thing I think the best, most common way that people are actually doing that. We're calling the inverse problem. Okay, the entire concept, meaning that I know the forward model quite well. By doing the backward model, okay, trying to solve the inverse problem remains really problematic. So there are, of course, if you're going to open some books and try to find those answers, you'll see people talk about high dimensionality and the probability of illumination or whatever. But I think they can actually sum it up in saying that you're trying to solve an inverse problem. Okay? It's usually either underdetermined, basically, or nonlinear or whatever, so it's problematic. Now, even though it's a hard problem, today you can see really beautiful results used in industry in many applications. And I'll show you in a second a few examples for that one. But actually, I'm interested in what you think about the last one. What do you think about the human, okay, the human eye vision system, the human vision system in general? Is it the perfect one? Do we want to imitate that one? This is our ultimate goal, yes or no? Remind you what Ramesh showed you in the second slide, something like that. I think that's the first thing that we actually want to show. So the human eye system has problems, okay? The way that we actually see, visualize, understand is maybe not the best way to do that. Now, for the version A you already saw. How about B? Which one is darker, A or B? Same. Why is the same? By the way, do you know? How come? What happens in the human's vision system that causes us to think that A is going to be darker? We are not trained to look at absolute values. The human vision system looks at relations. So because the color to the next, to the box that's next to it, okay, are different, this is what we feel. By the way, not just for vision, also for temperature, feelings, and so on. Let's go for number D. How many red X's are there? 4, how many red X's are here? Hard to see, okay? So the human vision system is great, okay, but it's not perfect, okay? So we may not want to imitate it exactly as it is. So before we continue, I have to mention that those slides that I'm currently showing are coming from the book. Let me go back for a second to the slides. Coming from the book called Algorithm and Application by Richard Sinsky. He's a senior researcher in Microsoft Research. He's affiliated to Washington. There are many great books about computer vision. Okay, I really recommend that one because it came out, I think, like 2 years ago or something like that. So it has a lot of new algorithms and tricks along the way. So if you have time, spare time in the evenings, and want to read something a little bit about the algorithms and what is going on behind the scenes, I really recommend that book. So that slide was taken from this book. Now I'm just going to show you, for example, what is done today with computer vision in industry. Okay, let's take a few examples. So OCR, Object Character Recognition, okay, something that people did 30 years ago. I think it started in Bell Labs, when they tried to find out what is the zip code for the letters. I dare to say that it is a solved problem, okay? We know how to do that almost perfectly, meaning that if the computer was going to be wrong, I promise you, you are going to be wrong, okay? Trying to figure out what is the character that you're trying to figure out. Now, why is it so simple to do that today? Because think about it, there is only 10 letters, that's it, but you can actually insert into the machine billions of examples to learn out of that one. So it's a very easy problem to do. On option B, we see, for example, what happens when you would like to check to check in the industry whether the outcome of some fabrication system, whether it was correct or there was some problem along the way. You can do that also for low-tech and for high-tech. So this, for example, for low-tech. High-tech, it is done today in silicon processes, trying to figure out whether you printed the correct circuit or not, whether there was a disconnection somewhere along the way. We can do it for marketing. Medical imaging, okay, that's my favorite one, okay? It's a monster, medical imaging. What you have here is big data. You have huge data over time, same person. Think, for example, just how many pixels appear in one MRI image. MRI images of the brain. We have volumetric data. The resolution, roughly something like 500 by 500 by 128. We're talking about billions of data points and trying to analyze, trying to figure out what changed, how come. So today it is done to localize some of the problems or figure out what is going on for the same person over time. Basically, it has all the tricks that we see in a in traditional computer vision, but for volumes. Power industry. Okay, actually I'm going to talk about that system is called I think it's called the AWS, but I think that today we are no other system which will I think even much better than that one. Mobileye, a company worth billions. Actually, I think they have a contract with Volvo already working in the new models that actually has a small camera in front of the car, and when someone runs in front of it, it's going to do automatic stop, for example. Google Car, okay, a concept started from Sebastian Thrun from Stanford, basically, bought a few years ago, the ability to drive alone. Okay, I don't know if you're familiar with those challenges. Today, cars can drive alone in the city. Okay, Google Cars is doing that. Maybe we're going to see that in the next future. And part of that one comes from specifically just from computer vision. And here's another small example for surveillance. Those problems are super simple. I will wrap up. Okay, but skip this one. So if I would like, for example, to take a look what happened from the last 40 years in computer vision in general, so different problems came along those years. Bear in mind that 40 years ago, people talked about curves and surfaces, and then a little bit later talked about shape from something. Give me several images. Let's see if we can get the geometry. But most interesting is what happens around 2005 and above. Learning came into process, meaning that we have a lot of data. And out of those images, we would like to learn and be able to understand what do we see. If you're going to go to see what happened in SIGGRAPH application, SIGGRAPH is the main conference journal paper of computer vision. You're going to see that almost everybody are talking about big data and learning in order to actually understand what you actually see. Those are the main open problems that we actually have to face. Now, if, like I said, if you're going to be bored and just open one of the books, so for example, what you will see is roughly, let's say, 15 topics. Try to cover all the important parts of computer vision. Just going over some of those relevant parts. You will see about, people talk about image processing. So let's sharpen the image, make it, find the edges. Let's see what is going on over there. Instagram. Yes. Features. Even, for example, you would like to stitch a few images. How do you do that? You need to find what is similar in all those images. So we need to find descriptors, local descriptors, like sift and surf. So we're going to talk about number 4. We'll talk about features, segmentation. That's the major part that was improved by the Kinect. If you have some image, okay, take a picture of me. Try to extract me out of the board. You might be able to do this just for the image. Maybe. What happens if I'm going to stand outside now in a different background? What happens if the background was black? Good luck doing that. But with the Kinect, we've got new information. So now we have depths, you can do the extraction. That was actually the main key why the Kinect was such a huge success. Just even extracting the form from the background. So it's a very hard problem. We can talk about 3D structure, motion estimation, computational photography. The entire concept actually of Ramesh's lab here is the ability to add hardware to software together to manipulate the lenses along the way. We can talk about 3D shapes. Actually, that's my own expertise. Meaning that once you actually have the 3D shape, what can we do with that one? Whether it's rigid or non-rigid, can we actually understand what is going on from the 3D shape itself that you actually capture? And the last one, which we're actually going to talk about it, but not today, about recognition, for example. So you have an image, I would like to find the human, the face, figure out what is going on, what is the mimics. Can you do it directly for the images? So I think that one of the coolest applications came like 20 years ago, 2015, of Viola Jones' algorithm. They basically showed us how we can actually learn how faces look like and find them in the image. Today in the camera, you just use your iPhone or Samsung or whatever, your Android, and you actually find the faces and auto zoom on that one. How does it find the face so fast? Okay, so those are algorithms that we might have time actually to look into the details how it actually happens. So it's another option. So the last 2 minutes I'm going to spend is just to talk to you a little bit about OpenCV. So you do not really need to know how to program all those algorithms. All those algorithms are, like, think about it, like 40 years of hard work people shoved into, let's say. We will not be able to do that in this course, but lucky for you, will not have to do that. There is a library called OpenCV when almost all the algorithms or all the algorithms that you need for this course were already implemented. Okay? Now, it has an API for both C, C++, Python, MATLAB, but relevance for us probably is going to be C++. Just to give you an example, what that's great. So you can go to that site over there. You can find all the documents that you actually need to program any computer vision stuff with it. It's relevant for all platforms, including the Android. Okay, no problem with that one. It's divided to different modules. You're going to find a lot of examples for each one of the things that you want. Let me give you just 3 super fast examples. Let's assume that you would have an image you would like to find its edges. Why? Because you need it to separate, I don't know, whatever, something forward for background. Then you're going to get to a page. It will tell you, okay, so here's a function called Kenny. This is what it gets in input. Here are some explanations. What are the parameters of the functions? And they're going to give you a short example. So here is, for example, a simple code, just find the edges. Without actually understanding what is Sobel, what is gradient, you don't really need to know that for this course. So for example, we create a data variable, we call it source gray, whatever. It's going to be the pictures. We're going to create a few variables with some of the threshold that we want to use. We're going to run a blur function, so actually blur some convolution with the Gaussian, so you know how to blur. And then you're just going to run Kenny. That's it. Put the information of the image, of the input image, the output image. I'm going to use the same, so I'll destroy the old information. In this example, put some threshold, and that's it. Now, what happens if you want to do something more complex? For example, half transform. I need 60 seconds. For example, half transform. You want to find straight lines. Why? For example, a self-driving car. Exactly same trick. You just boil down to one line of function. You've got a beautiful code that actually find in real time the straight lines. This is basically what is done in Mobile Eye, by the way. The same algorithm to find where is the road. Nothing more than that. Just do a half transform for that. And what happens if you want to do some more complex applications? Let's assume you want to do some face detection to whatever. Is it harder? So exactly the same concept. What you actually do here is load what is known as cascade, meaning that OpenCV already learned everything that actually you need to know about finding the face. So the learning part was done a priori to your program. And in the end, it boils down to, again, just one line, okay? Just shove in your program, and the output will be the location for all the faces. So it's going to be good enough, okay? So even if you don't have any expertise in computer vision, you're able to run and do all the coolest stuff that actually you see.
And do it on various platforms.
That's it.
On mobile phones or corresponding libraries. Thanks, Dan. Now we're going to switch over to yourself and tell us. I'll try to do pretty quick 5 to 10 minute overview of
the lens that you look at. I'm an entrepreneur. Started 6 companies. Okay. Hopefully one of these lectures will be with a Google Hangout. Yeah. All right. So I'm a former entrepreneur. I started 6 companies before becoming a venture capitalist. I'm now a general partner at a firm called Northridge. We're the second largest venture capital firm in the Boston area. We're by Coastal, manage about $3.5 billion. So pretty sizable firm, and fund a lot of companies that you might be aware of. The graphic side, things like SolidWorks, and or things that predated that, and more newer projects, things like Quora that you might be basis. But back when I was an entrepreneur and I was in my early 20s, I did some things with computer graphics. I was my first parametric modeling packages. I worked on semiconductors. I worked on other hardware projects, and I learned pretty quickly that you can spend the same amount of time building something that's going to end up with high ground, or something that's going to end up essentially in a technology treadmill. And so the advice I want to give you in the next few minutes is a super summarized version of what can you do to not end up in a treadmill. Because in a treadmill, usually a startup never wins, or a small group of people never win. It's a company like Samsung, or a large behemoth that ends up winning. So, and it's the same amount of work. So I'll go through this for a few minutes. So with the winning, you've got to ask yourself a lot of questions. Are you too early or too late? What's the right timing to start a project? How can you build credibility? I think when you're starting a company, everything is about building credibility. Everything that you're doing. It's kind of like the constant pursuit of that. It's about how you extract long-term gross margins that are high gross margins, where it's very difficult for a competitor to displace you. And setting things up as you build your product so that you can leverage others and get scale. In terms of the context of our course, you all know smartphones have pretty much taken over. They're kind of at a mature state now. We're selling 1 billion smartphones a year, and about 20 million high-end cameras a year. The camera side is about $20 billion in sales, but it's a closed system. You really can't do much with a Nikon SLR. It's just kind of, it's like a mini computer. Back when the backs of devices existed. This predates you guys, most of you guys. But in a smartphone, you can do all sorts of stuff. So you can envision, I think, in the future, these products are going to look more like this Lytro camera, but you know, they'll tether the Bluetooth to your smartphone, and you'll do all sorts of stuff on your smartphone, and you might have, you know, just a sensor package on the lenses if you want to do night photography.
Sony just released
a product. Yeah. I think that's a great vision for the future of photography. I'm going to show you just some pictures of some frameworks, and I'm happy to spend time with you separately to understand them. And you know, if you were taking classes at HBS or at Sloan, you'd learn these in more detail. This is something called the Gartner hype cycle, and it's interesting to note that when you correlate back when different companies are started, you can, you know, this is the best time to start a company when things are. So let me just step back. The hype cycle measures sort of the hype on the y-axis versus time on a product as it gets launched. When a new revolution happens, something like Google Glass, you know, I would say we're up here, now starting to come down on this curve. And this is kind of the best time to start a company, right here. Is when everybody thinks it's stupid. The best time to have invested in Twitter is when people thought that it was just a thing to like send pictures of whatever you had for lunch that day back in 2009 or 8. So this is kind of like the best time. Now another way to look at it is there's a lady named Carlotta Paris who wrote a great book. If you want to learn about kind of dynamics of bubbles, which is when kind of financial capital and production capital dissociate, there's this great book. It's called Technological Revolutions of Financial Capital, and it's a very quick read. And this lady kind of published this graph in the 70s, and you've got this decoupling of financial capital and production capital that happens when valuations get out of control and all stuff, and you usually have a crash. And so you have two periods, an installation period of a new technology and a deployment period. There's two times to start a company and make big money. One is sort of in an installation period around the eruption phase, and people will pay exorbitant amounts of price for something that's interesting because they can see this inflection that's going to happen. And I think it's going to be probably, if you step back, Google Glass is going to get launched commercially probably next spring. It will probably be subsidized by carriers. You'll be able to get $200, $300, $400, and it'll get some level of adoption. And the first apps that are going to be on that deck are going to get lots of traction. If you're in that deck and you have interesting stuff and you build a killer app, you're going to be able to, as a founder, get crazy prices for the value of your startup. We already saw this in smartphones. I would say this is the phase that Mr. Graham was created at. And, then you have this crash that eventually happens when valuations kind of catch up to financial reality. Then you have more of a fast follower, harder to do startup. If you're a hacker and a hustler, it's harder to start a company in this turning point, because it's usually the serial entrepreneurs and people that really can amass a lot of resources that can get stuff to happen. So, 2 minutes here. This is a framework to look at how you build competitive differentiation. You could either differentiate based on best product, differentiate based on total customer solution, or system lock-in. Best product would be something like low cost or more features. Usually that's really not the best place to go. If you think about where the magic happens in comfort zones for engineers, comfort zone for people are, I'm going to just have a patent on this, or I'm going to have more megapixels than the other guy, or more this or more that, and that's just like a treadmill. It's not the place to be. You really want to be in system lock-in, where externalities lock you in, and you end up with barriers to entry that are sustainable and long-term. And I think that's where the magic happens. So if you think about an app store, a platform, things with network effect, where essentially get external parties that create switching costs for the product or the app that you're launching. 2 or 3 examples. We think of Uber, they're creating a marketplace. Marketplace is a great system lock-in. This company, Tile, I won't get into the video because we don't have time, but if you go, it's a little RFID tag that you put on all your stuff so you don't lose your stuff and you can find it. It doesn't need a battery, so they're great. But they're really using your smartphone to keep track of all this stuff. Lose your product, if you lose whatever you had a tag on, everybody's smartphone that has ever purchased a Tile becomes a locator. So if a thief is walking around with your stuff, and I might just be at the same store as the thief is at, I can help the guy that lost his stuff because my smartphone's going to send a message. So that's network effect. Building things like this into hardware create very strong switching costs. Another company that's a startup in the hardware space, a company called Oculus Rift, that's working on pretty cool VR system. I don't know how many people have heard of this company. Great. When Brendan started this company, his focus was entirely on the developer side. The reason they're going to probably win is because he built Scaleform, which was the main tool to do the UX for video games, and he had 80% share in that business in 3D video games. And so he's got great relationships in the developer community, and he's going to build a platform. So finally, Leap Motion like this. I don't know if they'll succeed or not, but they've got this airspace section. Again, they're trying to build apps for their system. Once developers make an investment into it, it's hard for them to replicate that investment into somebody else. Of course, Apple or someone else could, or Microsoft could try to really introduce their own version of it, and then blow them out of the water, but yeah, just trying to their own version. So again, I just want to leave you with my view that this is really a spectacular time to start something in computational photography, or more specifically in augmented stuff. I think Glass is really going to be a platform that worked for 3 months and have. I think there's something there. It reminds me of kind of the early versions of Android when Rich Miner was working on the first, kind of the early days of computers. So. Yeah. Cool. All right. So build this when you're thinking of your apps as part of this course, and you of course need to have a product that's beautiful and exciting. But if you don't have system lock-in as part of yours, as well, it's going to be hard for you to kind of build something that's going to be difficult. Awesome. Great.
Rick and Rick will be here. We'll wrap up with the first video, which is we have less time than we thought we would. We'll give a quick overview. You see, we have a number of folks. If you are interested in going to Montana, collaborate with some of those folks who have the semester, and just go over there and continue. And please email me. So we'll do a hackathon here. We'd like to do all these guys were here last summer. They know him. Tell me, J1. Everybody knows the Facebook page. Website is MIT Platform. Need a separate one for online.
Okay, we're going to talk very, very briefly about Android development. How many of you have developed for Android before? Okay, so a good group. How many of you have an Android device to develop on? Good, great. How many of you didn't set up saw the instructions yesterday to set up your own environment? Good. Okay. So it looks like you're all a little bit up to speed and you're familiar with the environment. I'm going to give you a big overview, and then I'll give you some more details on the assignment. Assignment will be open book. We want you to use the same resources that you would be using in real life, and that includes libraries, that includes Stack Overview. Right? So, what you're programming in Android is the Eclipse IDE. Now, there is a new IDE coming out, which could use things quite a bit, but for now, we're going to stick with Eclipse because that's where all the documentation is, and that's where people are familiar with. So, if you haven't used Eclipse before, your file structure is on the left, right here, and this is your main window. There's a console. What you want to look for Android are these two buttons up top. This is your SDK downloader. This is your device manager. And then, more importantly, on the right here, this little flying Android on the right is the log cat. And what that is that's a live log of the data. So you can see what happens as you're developing and you can debug it. So, I'll give a quick overview of the device manager because that's going to be a problem that some of you might encounter. So Android has two ways to test your app. One, you can plug your phone in directly via USB. And secondly, you can run it through the emulator. Now, I recommend that you plug it in through your phone if you have a phone because it runs a lot quicker, it's a lot faster development cycle, you can keep compiling everything in there. If you would like to, if you don't have an Android phone, you'll have to use the emulator. It's very slow, especially to boot. It takes about 30 seconds to boot the emulator computer, and it sort of slows down the time every time you want to run the program. So as you plug it in, as you plug in your device, hopefully your PC or computer will recognize the drivers, and it will show up here. And that'll show when you want to run your program. So I'll open up example right here, and so you can see what the file structure is like. And that should be good enough for you guys to get started on your assignment. So on the left, we have the big things you have to note are assets, resources, libs, and source, and then the manifest. So five things we have here. Assets is essentially if you want to bring in a database or an external data, you put it in the assets folder. Okay? You don't need it for this first assignment, but you might need it in the future. It's good to know you're going to drop it in the assets folder. Your libs folder is for any external libraries. Please use external libraries, okay? Don't reinvent the wheel here. We're trying to create cool apps. Don't let things slow you down. That's why we have a lot of emphasis on OpenCV, OpenNI. They've already done it for you. Welcome to use libraries for a lot of these assignments. And the source is where your main code goes, and the last part is Android manifest. I'll show you what the Android manifest looks like. It's essentially XML, and what it does is it's basically the root instruction manual for your app. And it tells the app, it tells Android what permissions you need to use and what access to hardware you need. So in this case, what you're going to be building is a flashlight app. You turn on the LED flashlight, and if you don't have an LED flashlight, you'll have to just change the screen color. Pretty basic, but you'll have to do things in the Android manifest to do that. And that's where you'll be setting a lot of your user permissions. So again, very easy. It's just a copy and paste, a couple of permissions, and you're done.
And we will post the exact instructions for this one.
Right. Absolutely. So the main files you'll be manipulating are under layout and under your actual source. So these are the three files you'll need to make this first app. The layout file runs through a layout Android layout editor. It works, it's hit or miss, it depends how complex your UI is. For this, it's perfect. You're just dragging a button on, and you should be able to interact with it easily. And it's all sorted in these folders here: layouts, composite, images, data, time, date. You're just using a button, a text label, and you should be able to start the flashlight from there. But if you do need to get a little bit more complicated, or you want to interact with the data a little bit better, there's a tab here at the bottom, which lets you see the raw XML. So that's how Android builds the UIs from this raw XML data. It's all hierarchical, and you'll structure everything in layouts. So there's relative layouts, absolute layouts, which I'm sure you guys are familiar with. Absolute is you hard code in exactly where a button is supposed to appear. Relative is something above it, below it, to the side, etc. And then the last file you'll need is obviously your Java source code. So, real quick rundown. It's very, very similar. If you've done Java before, this will all look very familiar to you. The things that you need to know are right under your class definition, you have your local variables, which you'll have to instantiate yourself. You have the onCreate function, you have the onStop function, and you have onCreate options. Those are some time generated for you. Android goes through what's called a life cycle. So every time you open an app, there's a sequence of events that happen. So for example, you create the app, you start the app, and then you resume it. All of those functions are run before the app is resumed. And when you quit out of an app, the onStop function. So you have to do things to handle that appropriately. Now, to build this flashlight app, you're going to have to turn on the camera, because that's how you trick the Android phone to let you get access to the LED flashlight, right? But you don't want to keep that camera running, because only one app can handle the camera at a time. So when you leave the app, you're going to have to shut the camera off. It's very simple code, but those are the things you have to take into account when you're programming for Android. And I assure you that if you make this mistake, your phone will die really, really quickly. Your app will be using so much power, your phone will die. So you'll know when you make a mistake when you program the app yourself.
And then maybe describe how this
Right. So we are going to, you can develop for Glass for two ways: the RESTful API way or the APK way. The APK way is far superior for everything we're going to do here, and it's where Android is going eventually. So you'll be designing these APK files in Android, package up the APKs, and during office hours or during class, you'll be able to put them on the class yourself and see how you can interact with them. And the emulator is actually a very good first use case to see how you can interact with it already. So seeing it on Glass is just a good way to see how you can interact with it. So that's where we're going with this. We're not going to get too complicated in Android because, again, we have the libraries to do so. But it's important to understand how Android is laid out so you don't spend too much time. Okay?
Good. So that's a very quick overview, of course, just like many other things. So it's Firefox.
course about cameras, technologies, how to use the community, how to use the machine learning on the devices, computer vision tools, Android tools, some of the optical and sensor technologies, as well as how you might configure the app and when's the right time to launch it, of the app ecosystem. That was a lot for class, but that's the point. We want to get all the ideas across. And we will be posting office hours. We still have to figure out some of the logistics of that. So Rohan, Nikhil, and Daniel will be available for there may be some, initially there might be some bumps available. Make sure about the Facebook page. If you're not registered, send us a call. That's the website. Class. Any quick questions? Yes.
Can you explain the difference?
So 131 is undergrad, 531 is grad version. So the only difference is that it's from 8 assignments to 6. And your grading. Excellent.